Okay, and continuing our KSP discussion, also known as solubility equilibrium, we're going to focus in on the fourth type of KSP problem. Which salt precipitates first? So in these scenarios, you're going to have a mixture that contains ions, and you're going to take a second solution and slowly add it to the original solution, and you're going to cause a precipitate to form. And the addition of the second solution will cause one precipitate to form first and then a second precipitate to form after that one. And it depends upon how soluble those two potential solids are. The one that is lower in solubility is going to be the one to precipitate out. So our goal in these problems is to calculate the equilibrium ion concentration needed to start precipitation of each salt. And whichever salt requires the lowest equilibrium ion concentration is the first one to precipitate. So this is often referred to as selective precipitation because we're making only one salt precipitate, okay, and we're able to remove that ion from that solution through this selective process and leave all the other ions behind in the original solution. So let's take a look at some problems. Number 11 here. You're taking 20 milliliters of 0.01 molar magnesium nitrate solution. Okay, so that's aqueous. Even though they don't say the word aqueous or the word solution, I have a capital M and I know molarity is only for solutions. 10 milliliters of 0.01 molar zinc chloride. So again, that's aqueous. And we're going to take some sodium hydroxide and slowly add it to the mixture. So let's pause there before I move any further. Let's get a picture of what's happening. We're taking 20 milliliters of magnesium nitrate. So we have water. Inside of there we got magnesium ions, nitrate ions floating around. And then we're mixing it with zinc chloride solution. So I got zinc ions and we got chloride ions floating around in the solution. We mixed together these two solutions, so the volume is now a little bit bigger. The total volume, those 20 milliliters plus 10 mils, our total volume is 30 mils. Right? Essentially, we are diluting these two mixtures as we pour them together. So something to keep in mind further along in this problem, the molarity of the magnesium nitrate is no longer 0.01 molar. We're going to have to dilute that concentration eventually, and the same thing applies to that zinc chloride. Anytime you mix solutions together or add water or change the volume, you're diluting the solution, so we're going to have to calculate a new molarity, but save that for later. Next step, sodium hydroxide is slowly added to this mixture. Okay, so in a separate container, we have sodium hydroxide solution, and we're pouring it very ever slowly into the original beaker. And so as we add this solution, the sodium and the hydroxide ions are going to start to interact with our original ions in solution. The hydroxide is the important ion here because the sodium, I know, is always soluble, so it doesn't make any precipitates. What we care about is the hydroxide as it's added to the solution. Now, hydroxide, when it pairs up with the magnesium, a possible solid magnesium precipitate, it can form. Okay, because that's roughly insoluble. Look at its KSP value. It's 6.0 times 10 to the negative 12. Wow, that's pretty darn insoluble. Okay. Another possibility for hydroxide is that it's going to form a precipitate with the zinc 2+ ion. And its KSP value is 4.0 times 10 to the negative 17. Also pretty darn insoluble. So the question becomes, if these are the two options for the hydroxide, which one is the first to occur? Because Not both are going to occur simultaneously because we're adding the hydroxide very, very, very slowly. And as it mulls around in the solution, it's going to cause only one of these salts to precipitate. Then once that precipitate forms, okay, we can filter it out and then continue to add the hydroxide and make the second precipitate form. Okay, so our question is, how much hydroxide is needed to make the magnesium hydroxide form, and how much hydroxide is needed to make the zinc hydroxide form? And whichever one requires a lower amount of hydroxide, that's the first one whose requirement is met first, and that is the first solid to precipitate out of solution. So is the magnesium going to form magnesium hydroxide solid, or is it going to be the zinc hydroxide? So we want to first start by writing our dissociation equation. For the magnesium hydroxide. And we're going to do the same thing for the zinc hydroxide. Okay, let's start by writing our KSP expressions. Okay, so we want to solve for the hydroxide ion concentration in each one of these scenarios. Okay, we want to solve for the equilibrium hydroxide concentration for the magnesium hydroxide and then repeat for the zinc hydroxide. So the KSP number was given to me for both of these, so that's just a straight plug and chug. We're solving for the hydroxide, we're going to leave that as our unknown. But before I can plug magnesium ion concentration into the KSP expression, I first have to calculate it. Because if I look at the original problem, it originally was 0.01 molar when the volume was 20 mils. But then we added the zinc chloride solution to it, and so we've changed the total volume to 30 milliliters. So anytime that we change the volume of a solution, we've diluted, or we're going to have to calculate the new molarity. So when we mix those two solutions together, we've essentially diluted both of these solutions because we've increased the total volume. So that's our first step, is to calculate the new molarity of the magnesium ion and calculate the new molarity of the zinc ion. So we can do that real quickly. And there's a couple ways you can go about this. You can use the dilution formula, M1V1 equals M2V2. That's perfectly fine. Or you can think about it this way. Okay, well, how many moles of magnesium ion are there? Divided by the total volume. And so how many moles of magnesium ions are actually there? Well, where did the magnesium ions come from? They came from the 20 milliliters, or 0.02 liters. And that solution had a molarity of 0.01 molar. So that means you have 2 times 10 to the negative 4 moles of magnesium nitrate that were originally added to this mixture. So that means you got 2 times 10 to the negative 4 moles of magnesium 2 plus ions. And so the molarity of the magnesium 2 plus ions is 2 times 10 to the negative 4 moles of magnesium over the new volume of 0.03 liters. And so the molarity of the magnesium is 6.67 times 10 to the negative 3 molar. Perfect. Okay, and I'm going to plug that into the KSP expression. For the zinc chloride, okay, I could repeat the same process. Okay, or I can use a dilution formula, so I'll show you the other alternative. You can use M1V1 equals M2V2. So the original molarity of the zinc chloride is a 0.001 molar. The original volume is 10 mils. We don't know M2, but the new volume I know is 30 mils. So you solve for M2. The diluted molarity of the zinc ions is 3.33 times 10 to the negative 4 molar. Okay, so we're going to take these numbers, 3.33 times 10 to the negative 4 molar zinc, plug that into the zinc ion concentration of KSP, and then we're going to do the same thing for the magnesium, 6.67 times 10 to the negative 3. Alright, so now it becomes plug and chug and a little algebra. Plug in the KSP of magnesium hydroxide that was given to me. It is 6.0 times 10 to the negative 12. We just solved for the magnesium concentration. That was 6.67 times 10 to the negative 3 molar. And we don't know the concentration of hydroxide. That becomes our unknown. Okay, so let's solve for the concentration of hydroxide. Hydroxide ion concentration at equilibrium is 3.0 times 10 to the negative 5 molar. So what this value means is that in order to start precipitating the magnesium hydroxide, the concentration of hydroxide needed to do that is 3 times 10 to the negative 5 molar. So we're going to repeat this process for the zinc hydroxide. Zinc hydroxide had a KSP value of 4 times 10 to the negative 17. Okay. We just saw for the zinc concentration above, it was 3.33 times 10 to the negative 4 molar. Again, we don't know hydroxide. That's what we're solving for. I get a hydroxide concentration of 3.5 times 10 to the negative 7 molar. Okay, so I have two possible answers for hydroxide. Is it the 3 times 10 to the negative 5 value or the 3.5 times 10 to the negative 7 value? You always go with the lower molarity, meaning that the zinc hydroxide requirement of 3.5 times 10 to the negative 7 is going to be met before the magnesium hydroxide requirement of 3 times 10 to the negative 5, because this 10 to the negative 7 is a smaller value and it will be met first as that hydroxide is being slowly added. So the answer for letter A is zinc hydroxide. And then letter B, what is the hydroxide concentration when the first precipitate begins to form? This is the answer for letter B. And so letter A, zinc hydroxide precipitates first. And you can say because zinc hydroxide requires less hydroxide than the magnesium hydroxide. So to recap, we started with the solution containing some ions and no precipitate formed because there was no insoluble combination. But we then took a second solution and slowly added it to the original solution, and that second solution contained some hydroxide ions which would pair up with some magnesium and cause a solid, and the hydroxide could also pair up with the zinc to cause a solid precipitate to form. The real question is how much hydroxide is needed for each precipitation reaction to occur. So you took your salts and wrote out the dissociation equation for each one. You wrote their KSP expressions. You plugged in the KSP number given to you. you plug in the original or the diluted molarity of the magnesium and for the zinc, and then you solved for the hydroxide ion concentration in each scenario. The one with the lower hydroxide ion concentration would cause that precipitate to form first.